Today, I'm going to show you Quartic AI's process development optimization application and how it combines machine learning with subject matter expertise to efficiently explore the design and operation space while continuously recommending experimental settings. This results in determining optimal recipes in far fewer runs than traditional methods. The application also serves as an effective knowledge management tool by managing all of the data coming out of these experiments, so combining process, quality, and PAT data to create a holistic view of the PD space. Connecting to and integrating the lab equipment and systems, digitally managing all of this information not just for a single experiment, but for all experiments, multiple runs, multiple molecules, including work that your colleagues are doing as well. So gain visibility into all of this, be able to analyze it, and then carry this knowledge forward about the design space, about the operating limits and cliffs, CPP and CQA relationships, carry all of this knowledge forward through scale-up and tech transfer. So now I'm accelerating not only my experimental and development phase, but the entire product lifecycle. This also becomes the foundation for both quality by design and continued process verification programs. So let's go into the demo itself, and to set the stage, imagine I'm a chemist working in a small molecule lab, and my focus is to perform these experiments as efficiently as possible. So minimize the number of runs to get to my target product profile, and do so using this AI-driven PD optimizer. I'll start by showing some of the contextualization around my lab. So here's my lab space, some different process units, the individual pieces of equipment I have. So here's one particular benchtop reactor. And if I come into it, I'll be able to see all the data I have available for it. So on the right-hand side here, I have all the available data sources coming into the Quartic platform. On the left-hand side, these are the data sources specific to this reactor. So from this PLC, I have some streaming sensor data, temperature, pH, pressure. I also have lab-based sample data I'm pulling in, and spectral data that I can use for PAT to track things like my production peaks or particle sizes, whatever I need as I make adjustments throughout my experimentation process. And the data you have available will depend on the digital maturity of your lab space. So here we're connecting to the reactor PLC that's all networked so we can stream the data, but I could also work off of data exports, CSV files, or manually entered data if needed. And here I'm focusing on a reactor component, but this entire application is flexible and can be applied similarly across all your workflows and process units, whether it be granulators, crystallizers, dryers, etc. So now I'll come into the PD optimization application itself, and I can tie into any of those assets I've defined and connected to. So again, my asset, my spectral probe, and because I'm making a live connection and controlling the reactor settings in this case, I also have some handshake and heartbeat tags to monitor that live connectivity. So now that I have that asset configured, next I want to start a new project, and I want to work on ampicillin. These are some parameters specific to my starting equipment settings, so I'll enter these, I'll choose the material I'm working on, and then connect into my PLC. Once I have that connection, I'll be able to see all my different process parameters coming in, so in this case I just have 3 of them. And now I can configure the design space. So for each parameter, I define the upper and lower bounds, and optionally a starting value for my first run. And from here, the AI algorithm will take over and again, search through these upper and lower bounds in as few runs as possible to discover the optimal settings and search the entire design space. Then I'll probe my IR probe for a product sample, and here I can identify my production peak that I want to try to isolate and maximize, and any impurity peaks I have. So in this case, I have one off to the left here, and another off to the right, and I want to minimize these. So I'll see how my parameter setting adjustments in this operational space impact my output here, impact this IR spectra. So I'll get started with 10 runs to start. And as this is running, we'll see it iterate through and we'll be able to see these set point adjustments change with each iterative run. In this environment, we have a digital twin running in the background. So we can quickly iterate through multiple runs without needing to wait for actual lab-based experiments to be run. So if you have, or we can help build a digital twin for your process, then we can augment physical lab-based testing with in silico modeling. Essentially digital experimental runs, which will further accelerate this PD timeline and minimize the number of experiments that need to be run in the lab itself. If we don't have that, that's perfectly fine. We'll just run the experiment, get those results, feed them back into the optimizer, and then recommend the operational settings for the next run or the next time interval and continue to iterate through. After I have enough runs and enough data, I will also see a feature influence score. So for each parameter in my design space, I will get a percentage weighting for how much it impacts my output, my yield in this case, but it could also be for any other quality parameters as well. Now, because I'm using simulated data here, my data coming in is all almost identical, so I won't actually get these weightings, these influence scores, but they will be generated when running against an actual process. Now, at any point, if I see something I don't like, I want to reset a parameter or adjust my design space, I can always pause this optimization, pause this run, make any adjustments. So here I can adjust my upper and lower bounds, change a starting setting for the next run, and then resume my experiment. This is really meant to be an interactive, iterative tool. It's not once you set it up at the beginning, you're stuck in it, but you can make adjustments as you go through. This is where you can kind of tie in some of that subject matter expertise alongside the AI model that's running. Once this completes, I can then save off this project, conclude the experiment, and then come in and see the results either for this one or for other projects. So if I come in and look at amoxicillin, for an example, I can see the results for this too. I can export a report. I can view all the runs that have come in, as well as what my optimal run is here. And here's the optimal settings for this run 4, which was my optimal run. So now that I have these optimal settings, what can I do with it? Well, in terms of carrying this knowledge forward, from this experiment, I have these optimal settings. I can now go in and use this as a basis for additional runs. This could be used for several different things. It could be for validation of these settings. Make sure that if I use these settings multiple times, they consistently give me the output I expect, and if not, maybe identify any sources of variability that exist. Or maybe I want to try this for scaling up. I move from a 1 liter to a 5 liter reactor. Or maybe if I'm making a new molecule, I use this as a basis, as a starting point. So I'll come in, start a new campaign here, enter a name, choose my material, some settings specific to how I want to run this campaign. Then I'll save this off, which will take me back to the home page, and I can come in and configure some runs for this campaign. So I set up another run, give it a name, some equipment settings, and my output tag. And that's all I need now. I can start this, and this again is going to use those optimal settings that came from the design of experiment, run those through, and I'll be able to see what my results look like. To speed things up, I already have some completed runs of this other campaign, so I'll come in here and view it, and I can scroll through these, compare results across each individual run, perhaps look for that variability or any unexpected outcomes. But in this case, with simulated data, everything looks good, so now I can save this operational space back into the Quartic platform, where for my product, I can import all these different runs. So here we can see runs from PD. We see things coming in from Delta V, which is the manufacturing, the production scale things. So this now becomes a complete repository of all my data, all my runs, all my batches, starting off in PD, moving all the way up through full-scale production manufacturing. All my data, all that information, all that knowledge gets captured here, and it can always be referenced and used later. One other thing I'll say is here I've shown a Quartic integrated workflow. But this is all configurable and customizable as well. So we're using a Quartic ML model built in, but if you want to use your own ML model, or if you want to push results into another database or into an electronic lab notebook tool or some other reporting tool, all of that is possible as well. Likewise, the visualization, we're showing the IR chart, but if instead you have chromatographs, or you want to show parameter trends like temperature and flow rate, or even overlay those across multiple runs, this is all possible. This user interface is entirely customizable to your specific needs. So with that, I'd like to thank you for your time today. If you have any questions or would like to learn more about how Quartic's PD optimization tool can help accelerate your process and how it can be implemented, please reach out to us here at Quartic AI.